uh, the my goal in this video is to not come out as a teacher. Hello. In today's video of on quantum mechanics, I'm going to discuss something called step potential. Step potential is something which is we use to study reflectance, transmittance, and or coefficient of reflection, coefficient of transmission. And this is a very simple subject, but it's a, how do I say it? It is a gateway to something bigger. What's the bigger thing? So when we study this part called step potential, we understand something that when energy of the particle is less than the potential, then we find some unique thing, which is that the probability density of the particle inside the potential is non-zero. And that to me is one of the very interesting outcome of this experiment or this study, and that later takes us to a very interesting phenomenon of quantum mechanics, which is called quantum tunneling. So in this video, I don't think I will discuss quantum tunneling because it's a very long thing, and when I discuss something, I have to derive it completely, and it's a big thing. Quantum tunneling, I will tell you the formula of transmission coefficient, if I remember it correctly. I think that much I can tell you, but I don't think we can discuss the quantum tunneling in one video with the step potential. So this video I will do step potential. In the next video, whenever I'll do it, I'll make it on quantum tunneling. So let's come here. Let's discuss. So what is a step potential? What is a step potential? Well, few books have a subject written as step potential. Few books don't. Just for example, in Griffith, they don't have anything written as step potential. In the Griffith, they have a question. If I correctly remember, it's the second chapter of Griffith, and this is a question. There is a 1-star question that calculate the transmission coefficient of this system or something like that, or three. It is a 3-part question in Griffith. So Griffith hasn't solved it, but it has asked this question. It means it can be solvable. It's not very difficult. And if you go to Zetterle has solved it step by step. So I'm just giving you hints of where to look for if you wanna pursue some books. That's right. So how do we define the step potential? This is how we define it. It is 0 when x is less than or equal to 0, and it is a finite value v0 when x is greater than 0. This thing gives us a potential like this. If we make it our potential axis, which will tell us Vx, and if we make it our x-axis. Now how will this potential will look like? This potential will look like this, and this will go on till the infinity. This is the value of V0, and the potential will go on till the infinity, because x greater than 0 for all value the potential is V0. So now this is your potential. Okay, don't get fooled by this line. There is no end to this potential. In a step potential, there is no end. Now, what will happen? what will happen? Okay, the very first thing which we write is Schrodinger equation. Very simple, our Schrodinger equation very own. This is a part A, this is a part 1, this is a part 2. The question is divided into two parts of the potential, of the step potential. One is this part where potential is 0, and this is a part where potential is V0. In this part, when potential is 0, we have already solved this kind of question. Where? We have solved it in particle in a box. So the wave function for the first part we already know. What is that? That is, let's say, a e to the power I k1x plus b e to the power minus I k2x. Now think about it. This is one part, this is another part. This part of the wave goes along positive x direction. This part of the wave goes on negative x direction. It means this is our incident wave, this is our reflected wave. Got it? Very simple, and we are not even trying to make it complicated. Okay, now look at this. When a particle is coming at this potential, it can be of two types. One, for E greater than V0. Another case can be for E less than V0. There can be two cases. Now in the E less than V0, this is a case where we will do it later. We won't do it now. Later means after completing this. First case we are considering E greater than V0. So look at this. When the particle was coming at the potential well, or for the step potential, the particle would have some kind of momentum. So the momentum is what? 2me root over. That is the momentum. Now when particle enters this potential, if the energy of particle is more than the potential, so it will easily get through. It will easily get through the potential. Now our classical knowledge says that okay, it will get through very easily, and what will we have? We'll have a decrease in momentum, which is the initial momentum was root over of 2me. Now the momentum will be root over of 2m e minus v0. Very simple. So now when we write the Schrodinger equation, how will we write it? We have to write the Schrodinger equation now for E greater than V0 inside the second region. This is the first region, it is fixed. It is fixed. In the second region, how we'll calculate? We'll calculate this way. Plus V0 psi equal to E psi. Now this entire thing will become okay. Now here we define something called, okay, this part will be K1 also. I have mistakenly written K2. Okay, in this part, when we are writing K1, we also need to tell you that K1 is equal to root over of 2me by h bar square. Similarly, in this question, we have to define another K, which is K2. That is equal to 2m e minus v0 by h bar square, which will be this. Okay, now look at this. Isn't it the same kind of solution which we are looking for. Isn't it a same kind of solution that we have found here? Look at this. This is the same kind of equation. This is the same kind of solution. Yes. When we solve it using differential equation. So now the psi 2 will come out like this. C e to the power I k2x plus d e to the power minus I k2x. Now think about it. This is one which is going along this direction. This is a waveform which is coming out along the opposite direction. Now tell me, in the region 2, will we need a wave function like this? Will we need a wave function where E is in the negative direction? Because we already found our incident wave, we already found our reflected wave. Yes. So this is now unnecessary. After finding the solution, we can always assume that D to be 0. So if we assume D to be 0, this equation goes to this waveform goes to 0. So now psi 2 is only C e to the power I k2x. Remember, k2 is the momentum. K2 represents the momentum. Okay. When we calculate momentum, it is like h bar k. So when we are using this k2, it is giving us the value of momentum. Now for a waveform in second region, you need a momentum related to k2. So, and in the direction of positive, it means that this is nothing but your transmitted wave. This is incident wave, this is reflected wave, this is your transmitted wave. This is your transmitted wave. Okay, got it. Now what we do in every question on this kind of reflection, incidence, transmission, or particle in a box, all of this kind of question are they are always connected by the boundary conditions. So here also we'll have to apply boundary conditions. What are the boundary conditions? First boundary condition is, the first ever boundary condition here will be that psi in the region 1 at 0, because this is the origin, at 0 must be equal to psi 2 at 0. It is a very basic. Now this gives us a formula of what? A plus B equals to C. Now also we will find psi dash of 0 will also be equal to psi 2 dash of 0, which is the first derivative, or we can write it d psi 1 by dx, d is equal to d psi 2 by dx at x equal to 0. The question is not here ki x equal to 0 will always has to be obeyed. It has to be obeyed on the boundary. Now look, here the right side boundary is at infinity, so we don't care. This is at x equal to 0. So this is the only thing that we will care about. Now this will give us what? This is psi 1. When we will take a derivative, it will be ik all into a minus b is equal to ik1 a minus b is equal to c. When we take a derivative of it, what will happen? It will be I k2 c. Yes. Now that gives us what? A minus b equal to k2 by k1 into c. Okay. Now this is relation 1, this is relation 2. We can find easily A is equal to what? C by 2 1 plus k2 by k1, and b equal to what? C by 2, 1 minus k2 by k1. Got it? Got it. Okay. Now look at this. This is your incident wave, this is your reflected wave, this is your transmitted wave. For all the three waveforms, for all of these waves, we can find our current density. We can find our current density for all these waveforms. We call it probability current density. We call it probability current density. So now, okay, let me write it very well, in a very well manner. So J is calculated as h bar by 2im psi star del psi star or del psi by del x minus psi del psi star by del x. Okay. Now this was your incident wave. When we do the math for incident wave, what will we find? We find h bar by 2im. First you have to write psi star. Psi star will be a star e to the power minus I k1x into del psi by del x will be a into e to the power I k1x minus a e to the power I k1x into a star into a star. Okay, wait a minute. I miss something, I think. Yes, I missed this. There will be I k1. Now here it will be minus I k1 e to the power minus I k1x. Okay. Now look at this equation. This I k1x minus I k1x plus I k1x will go. This minus I k1x, this minus I k1x will go. What we are remained with? We are remained with h bar by 2im into a mod square into I k1 into 2. So 2 cancel, I cancel. What is the incident probability current density of incident wave? Which is this, nothing but this h bar k1 by m a square. Got it? Now let's calculate that for reflected wave, which will be h bar by 2im. We'll use this formula only. Now, what is the reflected waveform? This is the reflected waveform. Now we will use, okay, whatever will be here, it will be a minus sign. It will be of a minus sign. So let's start from there. Okay, let's write it. Why do it? Why do some kind of whatever here come, it will be minus I k1 and b will come out e to the power minus I k1x minus b will remain e to the power I k1 x minus I k1x. B will remain with I k1x plus b star will be here, and this will be I k1 e to the power I k1x. This good boy will be cancelled. This good boy and this good boy will be cancelled. What is remaining? What is remaining? H bar by 2im into b square whole into minus 2ik1. So 2 cancel. What is J probability current density of reflected wave will be minus h bar k1 by m b. I hope you understood this part. You understood this part and you have understood this part. Okay? I hope you understood this part and this part. Now we have to erase this part so that we can go to the further derivations of it. Alright? And I have to wipe it out. Okay. So, okay. Now we know that our transmitted wave is what? This is our transmitted wave. This is our transmitted wave. This is our transmitted wave. If I also remove this is our transmitted wave. Yes or no? Now we can calculate the Z trans for this. Look at this. This waveform is very much, it is exactly equal to the waveform that we had for incident wave. So whatever we calculated in this part to be our probability current density of incident particle, it will be exactly same, and in the K1 place we have to use K2, in the A place we have to use C. So now we found out H bar K2 by M C square. Got it? Okay. Now what we have to find? We have to find reflectance. Reflectance is the coefficient of reflection. Okay. Now the coefficient of reflection is calculated as Z reflection divided by Z incident. It is the ratio between the probability current density of the reflected particles or reflected wave with the incident wave. Now when we do this, what will we find? Okay, now what we do is, when we calculate it, we also calculate it in a way that we take the mod of it. Okay, so when we do this, we will find out that b square h bar k by k1 by m, h bar k1 by m will go up. So we will find is b square by a square. Okay, here look at this. This is our b, this is our a. When we take square of it, and when we take square of it, c by 2 will go. What will we be remained with? We will be remained with k1 minus k2 divided by k1 plus k2 square. Or we can also write it as, if we look at this. Okay, let's calculate transmittance first, then we will discuss this. So how the transmittance will be calculated? So it will be taken as c square by a square k2 by k1. Alright. Now, instead of a, if we use this formula, how it will come out? It will come out k2 by K1 into CC will be cancelled. CC will be cancelled. Here we will have 4 divided by 1 plus K2 by K1 whole square. So now if we take K1 common, K1 if you take LCM, then we will have 4 K1 K2 by K1 plus K2 whole square. This is your reflectance, this is your transmittance. There is a relation between these two. What are these? R plus T is equal to 1. R plus T is equal to 1. Okay. This is the formula. This is the formula. This is very easy, very simple. Nothing to worry about or nothing to think about. Now, what is the problematic part in this? And not the problematic part, but the exciting part here. What is the exciting part here? We can write this formula in very different way. We can write these formulas in a very different way. Look, K1 is denoted as your root over of 2me by h bar square. K2 is denoted as root over 2me minus v naught by h bar square. This is very much known to everybody. Now if we assume a term called K2 by K1 and we define it as this, root over of E minus V naught by E, which is basically root over of 1 minus V naught by E. Now this thing can change all this derivation very well, and it will be very suitable for us to deal with this kind of thing. And once we use root over here, we'll not have to worry about the squares anymore, or maybe we'll still have to use the squares. There is no substitute for that. This is how we do this kind of question. And remember, this is only the derivation of step potential where energy of the particle is more than the potential, the step potential. This is your reflectance, this is your reflectance, this is your transmittance, this is your entirety. And in case you are wondering how we transform the equations, I have to erase this part. Transform in a sense how we will change this equation into energy and potential term. Okay, I am erasing this part and I will do it here. Okay, so now look at this. Look at the reflectance formula. We can easily write reflectance as what? 1 minus K2 by K1 divided by whole square divided by 1 plus K2 by K1 whole square. Exactly same. Instead of K2 by K1, we can write this, we can put this formula there instead of K2 by K1. Now this formula can also be written as this term. This formula can also be written as this term. Now look, once you put K2 by K2 is equal to this, now this equation becomes root over of E minus root over of E minus V naught divided by root over of E plus root over of E minus V naught, entireties whole square. Got it? This is easier to calculate in exams. I mean, I've seen questions, many questions asked on this term. And now whatever even transmittance can be, you can simply say it's equal to 1 by r or 1 minus r and do it, but let's do it using this formula. Look at this. This is nothing but 4 k2 by k1 divided by 1 plus k2 by k1 whole square. Okay. Now instead of k2 by k1 we can write what? We can write 4 root over of e minus v naught by e divided by, this will be what? This will be what? Root over of e plus e minus v naught whole square, and the e part will go to the upward. The root over of e here will go to the upper part. Yes or no? Yes. It will become e. So now what you will have to write? You have to write transmittance is equal to 4 root e into e minus v by root over of e plus root over of e minus v naught whole square. Got it? Now that's basically your thing. Now here one more question that comes in this kind of numericals, and that question is what if E is very much greater than V naught? Well, in that case you have to only assume E minus V to be 0, and when E minus V when E is very much greater than V naught, you have to assume E minus V to be E. So if we do that, for E is very much greater than V naught, we'll basically write what? E minus V naught is close to E. So now this will be what? 2 root over of E whole square. When we do the whole square, what will happen? 2 square will be 4 will be cancelled. E root over of E, and here root over of E will be E, and here root over of E is whole square will be E. Now that will give us what? Transmittance will be equal to 1. If this is the case, then transmittance will be equal to 1. Transmittance will be equal to 1. Now this means what? This means there will be no reflection at all. There will be reflection coefficient will be 0 in that case. Reflection coefficient will be 0 in that case. And in that case also there will be one more thing. What is that? K2 by K1, look at. K2 by K1 will be what? E minus V will be equal to E. So this will be 1. It means what? It means what? It means that what we consider initially, that a particle will come, it will collide on a potential, and the potential will change its momentum. If the energy is too high, the change in momentum will not happen. Here, the change in momentum will not going to happen. It is K1 will be equal to K2. That's the thing. That's the potential step potential, and this is it. And there is one more thing, if I can remember, there is a part of this question where we have to solve it for e less than v naught. Well, I'll make another video for it, and yeah, I'll make another video for it. And because there is a lot of things, we have to define how the particle decays when it goes into the potential, and for that we have to calculate some, I think, penetration depth or something we have to calculate. And yeah, I mean, I can record it, but now I remember it. And in that case, your transmission coefficient will be 0. So people will think like, okay, transmission coefficient with 0, it means the particle will not enter the potential. But the probability density is not going 0. Probability density is getting 0, but exponentially. That part is interesting. I'll make another video for it. Yeah. I hope you enjoyed. Yeah. Thanks.